through the data collection process a little bit. I have a couple data collection sheets that one that I prepared and that I use typically, and then there's another one that was prepared, I believe, by the USDA that's a little more comprehensive. And I thought we would maybe go through both of those, and then you can kind of see what you like and use what you like. And then we'll look at what kind of energy savings opportunities we might be able to identify with pumps. And then I have some projects on here that we've done, and I'm going to talk about VFDs a little bit today too, and we'll talk about those more when we get to them. So anyway, just to get started, if I can get this to scroll through my slides. There we go. So when we're looking at collecting data for any type of system, but specifically pump systems is what we'll be talking about today. And I've just kind of listed some of the things that we need to get. And so first we want to get customer information. When we're doing ag energy management plans, or if I'm doing a report for you at utility, I need all the customer information to include in the report. And so on my data sheet, we'll see here in a minute, you can see how I've kind of outlined that. The other things that are really important on a pump system are pump motor information and actual pump information itself. A lot of times I will talk to a farmer or someone, or even a city people, when I look at city pumps. I'll ask them to give me the pump information, and they send me the information off the pump motor, which is part of it, but I don't get the information off of the pump itself. And so yesterday we looked at some direct drive or close coupled pumps, and it seems like the motor and the pump are just one unit. It kind of looks that way, and so they may think that they're giving us all the information when they give us the motor tag information, but that's not necessarily true. The other thing that we collect, besides the pump motor and pump information, is information on the irrigation system itself. And that way we can kind of compare how the pump is supposed to be operating based on what it's pumping to, maybe compared to how it is operating, and that gives us an idea as well. And then the other thing that I like to look at on my projects is the historic energy usage of the pump. We probably may or may not get that on our initial visits with the customer or producer. If we request it ahead of time, they may have it ready for us, or it's something that we can get later too. But that's really important when we look at pumps and pump energy use and energy savings opportunities. So with that, I think we'll just jump into looking at the data collection sheet. This is one that I put together and that I use, and the guys that work with me, they use it when we do field site visits. It may not be totally comprehensive, but it usually gives us the information that we need. And if there's something that we don't have a column for or a row for specifically, we usually get that in our notes or our facility sketch. And so that's just kind of an overview. The sheet is 2 pages, and I've shown both pages here on this slide. And so the left sheet is the front page, and we typically print them 2-sided, so we just have one piece of paper in our hand. And the sheet on the right with notes and the facility sketch is typically on the back. And I will upload this presentation. Of course, I'll bring copies of these information sheets next week too, and we can get those uploaded, and so everybody can see or have a copy if they'd like. So this is just the first half of the data collection sheet. With some of the work we do for utilities, we work with several different utilities, and so it just gives us an idea of which utility we're working with. And this is even useful if we're not working with the utility specifically or for the utility. We can reference who is the electricity provider for that pump if we get the utility name. And then the customer information is on the top left. It's just the general stuff that you would usually get. Name, address, phone number, cell number that's different. And something that we just started collecting more recently was email. There's a good number of farmers that we work with that don't use email, but there are others that do. And if they do, it sure is useful. It sure is nicer to be able to communicate that way and send draft reports back and forth instead of sending them through the mail. And then we just have a couple lines for a system description. For each farm, if you're looking at a farm with multiple pump systems, we want to be able to identify which pump system we're looking at in particular. And so most guys will usually have a name for different systems or a number, or they identify it somehow. I worked with one farmer in Idaho, and he had several of his pumps named as different philosophers, and I don't know where he got that idea, but I thought it was kind of funny, and so you never know what they'll do. But that way we can identify the system. The other thing we do is just kind of general information up on the top right-hand side. Just the date we're out there, the utility meter number, the utility meter number. Some of the utilities have a specific site ID number that they associate with the pump site or with a particular meter. And so if they have that, we'll get that. They may not always have that information, but every system should have a utility meter that's out there with a meter number on the front of the meter. And we get that information. So if we get the historical usage, we can make sure it's for the specific pump that we're looking at and that the meter numbers match up. Pump information. The top 3 lines are basically pump motor information. And so on the pump tag, I have some pictures of pump tags that I'll show here in a few minutes. But the nameplate horsepower is written right on the pump tag. Motor brand, that's just whether it's a General Electric or U.S. Motors motor or whatever the case may be. Motor RPM, that's all usually written on the pump or the motor tag as well. SF is motor service factor. And I usually like to get that just because some of these motors that we look at are sometimes operating overloaded. And that means that if it's a 100 horsepower motor, it may be actually operating at 110 horsepower. And the motors are usually designed to operate overloaded a little bit. They can handle that, but that's what that service factor tells us. And it's printed right on the motor nameplate, and it says SF, just like I've shown it here usually. So that's our motor information. Like I said, the pump's separate from the motor. So we need to get the pump information too. And sometimes it's harder to get, and it's always harder to get the motor information, I guess. The motor usually has a good nameplate on it. The pump may or may not. But we want to get the pump brand, pump model number, and with that information, we can get a pump curve for the pump. And we talked about pump curves yesterday. And if we perform an energy savings analysis, the pump curve is usually pretty critical to our analysis. We know what that pump's supposed to be doing compared to what it's actually doing based on field measurements or observed operating conditions. And so the other things, pumping flow rate, we may be able to measure that if we have the right equipment, or we can estimate what it is based on the irrigation system. For example, if you have the pump and he's pumping to one center pivot, we know that the center pivot is designed to at 1,000 gallons per minute, then that gives us a pretty good idea that the pumping flow rate somewhere around 1,000 gallons a minute. May not be exact, but we'd at least get ballpark. And then the discharge pressure, if the pump's running when we're out there and there's a pressure gauge or we have a pressure gauge, we can measure that. If it's not running, a lot of farmers will usually know what kind of pressure they usually operate at if they have pressure gauges by their pump. I have seen some systems where they don't have a pressure gauge and they just kind of guess what they think it is. It's better to have a measurement, or if they have a pretty good idea of what it is. If we're looking at a well, we talked yesterday about well pumps and surface water pumps. If it's a well, it'd be a good idea to know how deep the well is. I don't have specific line items on here. It'd also be good to know how deep the pump is set in the well. And then the pumping lift, of course, we talked about that yesterday. Surface water pump, we can measure that or estimate it pretty easy because we can see the water surface. If it's a well, we can measure that if we have the right equipment, or we can get an idea from the owner to what he thinks it might be if they measured it in the past. The next item, dealer, that's usually the pump dealer. And so if the guy doesn't have any information on his pump at all, but he knows who was the last person to work on it or who installed it, we like to write that down, and then we can give them a call and have them check their records, and then they can usually get us the pump information. And so that, a lot of times that's actually how we get it. They say, I don't have any idea what that pump is, but this such and such pump company installed it, and if you give them a call, they should know. And so that is pretty handy. The next line that we start, now this is half the sheet, and so water application is a whole section of equipment, and we'll see some on the next page. This first section is talking about wheel lines and hand lines. If they have wheel lines and hand lines on their system, we want to know the number of lines, how many sprinkler heads per line, and we can make notes if it varies, if they're not all the same, about how many acres they irrigate under wheel lines or hand lines, what their nozzle sizes are, and pressure. If they have an idea what their pressure is out of the lines, or if we measure it, we'll put that in here. Otherwise, we can leave that blank. If we know the nozzle size and an average operating pressure, we can estimate flow rates for the wheel lines and hand lines and get pretty close. Number of sets, that's the number of sets they have if they move the line across the field. And it varies depending on soil types and the line design and how many lines they have. How many hours per set, that's how long they leave that line sitting in one place watering, basically, before they move it to the next set. That's typically 12 hours or 24 hours, maybe slightly less or more depending on the operation. But typically, they're either moving the lines twice a day or once a day. They'll run it actually 23 hours is how long they run, and then they give them an hour to move if they're running what we would call a 24-hour set. Or if it's the other way, they'll typically run for 11 hours and then move, and then they'll move the lines morning and night. So, and then the age, this is something we really use for the utilities. It's a good idea to know how old the equipment is, how old the nozzles are in the gaskets, and that gives us an idea of how worn we could expect the equipment to be. If we could assume that our flow rates, or if it's new equipment, we could assume that our calculated flow rates based on nozzle size and pressure are pretty close. If it's 15 or 20-year-old equipment, we assume it's probably worn, and so we may not be able to estimate the flow rates as accurately based on the nozzle size and operating pressure. So that's the first half of that first page. This is the second half. This next section is specific for center pivots. If they have multiple pivots, we can write the pivot name or the pivot number, however they identify it, or however we want to identify it into these rows. What the design flow rate is for the pivot in gallons per minute, how many acres each pivot covers. The PSI here can either be actual operating pressure or design operating pressure. We like to get both if we can, but you can actually make a note of which one you've collected on the sheet. I don't really have a good place to write that note, but that's usually a good idea. And so usually when a center pivot sprinkler package is designed, it's designed to operate at a certain flow rate at a minimum certain pressure at the pivot point. So it may be 900 gallons per minute, and they want you to have 45 PSI at the pivot point to make it work well. And so that's what we would note here. Usually for pivots, a lot of farmers will just know what their design flow rate is for the pivots. They probably won't know the design operating pressure, but they may know what kind of pressure they usually have at the pivot point. A lot of pivots will have a sprinkler chart, and sometimes it's right in the pivot panel at the center point of the pivot. There will be a whole chart there, and you can pull those out, and they have all this information right on the chart. There may be something called a precipitation chart in the pivot panel. It tells you how much water you put down at certain speed settings with the pivot, and it'll usually have the design flow rate and operating pressure of the pivot written on it as well. And so we can get all this information. That percent setting, that's what they usually operate at. They usually have a dial or a digital control, and they can set it to run at 100% of full speed or 50% or anything in between 0 and 100. And so I try and get the setting that they usually operate at, how much water they're applying at that setting, and how many hours it takes for that pivot to complete a full revolution. And then again, we're just asking for the age of the sprinkler package here in that last column. Crop information, and this is can be for current crops or just their crop rotation in general. And so we may want to know if they have a mix of barley and alfalfa on their farm and potatoes. You can list each crop, list whether it's under hand lines, wheel lines, or center pivot, and when they usually, on average, start their irrigation on that crop, and when, on average, they're done. And so this kind of gives us an idea of how their water system works. There's just kind of a blank place for notes under crop rotation, and crop rotations may vary. In Montana, they may leave it in grass pasture for quite a while. You may have a system where you have hay in there for 5 years, and then you break it out and put some type of grain crop in for a couple of years and back in hay. In Idaho, we usually have the grain and potato and hay rotations. So they may go grain 2 years and potatoes a year, or switch off every other year. And so that's just something, the information we like to collect. The next section on flow, this could be average operating conditions, or this may be the operating conditions the day that we're out there. We'll talk about variable frequency drives and variable speed drives a little bit later. But this information really helps us out with those if we're going to evaluate a VFD. And so we want to know what their full flow rate is, how often they're running at that rate, and then which lines, if they have a center pivot and 4 wheel lines, full flow would probably be the center pivot and 4 lines. Then the reduced flow might be just the pivot operating alone or the wheel lines operating alone. And we try and get an idea of what percentage of the season that they operate under those conditions. And so, and a lot of guys will usually have a pretty good idea on this, how they operate. If you ask some of the right questions, you usually get to this point and get the information that we need. The recommended program participation, this is something that's more specific to utility-sponsored programs. A lot of utilities will offer rebates if farmers replace nozzles, gaskets, sprinkler heads, drains, sprinkler packages, that kind of stuff. And so this is just where we work with several different utilities. We just may look at the system. If there's something that's obvious that we would recommend on our initial site visit, we'll mark it here. If the sprinklers or the nozzles and gaskets are 20 years old, we would mark those. If the sprinkler package is really old, we've marked it probably needs to be replaced. And it just kind of depends on what we see on the system. The back page of the sheet is just for extra notes, and we usually like to sketch out the facility. And so we may just draw on here kind of in general which way is north, where the pump sits, which way the main line runs, what size the main line is. And I don't know. Yeah, I don't think I'll try drawing anything on here. That might be too involved, but it'd just be a general facility sketch. Sometimes I'll just hand a sheet of paper to the farmer and say, hey, you just kind of draw out your farm for me and show me where the pump is, where it sits in relation to your pivots and wheel lines, where your main lines run, and what size they are, and they'll sketch it out for me. And then I can at least take that back and look on Google Earth or an aerial photo and kind of see how it lays out and get more exact measurements that way. And so that works pretty good. This slide is a picture of a pump nameplate. This is a vertical turbine pump. Talked about those yesterday. I couldn't find a good picture of a centrifugal pump nameplate to show, but they would be kind of similar to this. So this gives us good information. If it's correct, it tells us who the manufacturer is. This is a Vertiline. It tells us the pump model number, the 10JKH. It gives us a serial number. I can't really do too much with that unless I actually call the manufacturer, and then he can give me all the pump information based on a serial number. But I usually jot it down, but I don't. I've only used it a few times, and I really couldn't find any other information. And this nameplate also tells us that this pump is designed to pump at 950 gallons per minute at a total dynamic head of 320 feet if it's operating at 1,800 RPM. And so that way I can grab a 10 JKH pump curve, and I can see how many stages it would take and what the trim would be to give me these operating conditions. We looked at pump curve programs a little bit yesterday. I can go right into the manufacturer's pump curve program and enter these numbers in. I can just enter probably the design operating conditions, 950 gallons a minute at 320 feet ahead, and tell it to go 1,800 RPM pump and tell it to go. And it'll probably come up with this model number as one of my options. And I can just select that pump, and I have the pump curve for the pump. This is a motor nameplate. This is a newer motor. They got a little bit off on their stamping, but you can still kind of read it. I was hoping it'd show up good on the slide. And it shows up good on my screen. I hope it shows up good on yours. But this is where we would get the pump motor information. That last tag was just for the pump itself. This one, for example, sometimes you have to kind of search to find the information you want. So this one, this is horsepower. This is a 200 horsepower motor. At 460 volts, it's a 460 volt, 230 amp motor. Service factor amps, it says 266. We talked about service factor a little bit. That's just showing you can overload it to the point where it's drawing 266 amps for short periods of time without damaging the motor, basically. A lot of times it's a good idea just to take a picture of this nameplate, and then when you get back in your office, you have all the information there. I also like to write it down just as a backup, just in case. This one tells us here's the speed in RPMs, 1,775 RPM is where that motor operates. Here's the service factor, and I think that probably says, it's hard to read in the picture, but it's 1.15, I'm pretty sure. It's a 60 hertz motor. This tells you the motor efficiency. That's the nominal efficiency. I think that says 93.6. The guaranteed efficiency is 92.4. This is all good information. We can use that in our energy savings calculations when we're doing an evaluation. So it's just good to get as much information as we can. This is another nameplate. This is on an older motor, and so it looks a little bit different. And this one's, these older ones can be harder to read because they usually have some type of calcium or other deposits on them, and sometimes you need to scrape them off. So this one shows the pump horsepower right here. It's a 150 horsepower pump. This is the RPM, 1,775 RPM. Service factor right here. You can't read that, but I know that that's what it is. It says 1.15. 460 volts. This motor will draw 168 amps. And this, a lot of the older nameplates won't actually give us pump efficiencies like that new one did, or motor efficiencies, excuse me, like that new nameplate gave us. It's probably a requirement that the new ones need to show what the efficiency is. It probably wasn't a requirement back in the day when these older motors were built. And so we don't get the same information. I just maybe pause right there for a minute and ask if there are any questions to this point. If not, we'll continue on. I was talking about this yesterday with some the guys I work with and some of my neighbors. It's tough giving a presentation over the computer because it's hard to see what people are doing, and I know I've been on the other end watching computer presentations, and so it's hard to give feedback and get feedback. So, but next week I'm glad that we'll be meeting face to face, and then we can if there are any, we'll be talking about some pump stuff next week too, so if there are any questions, we can cover them. But still, if you have questions right now, interrupt me as we're going through this.
Great. And
This is
reminder, you have to unmute yourself if you're going to, if you've muted yourself on your screen, you have to unmute yourself in order to let your voice be heard.
Right. That's a good point. So, yeah. Okay. This is a separate data collection sheet. This is either University of Wisconsin or USDA. I can't remember who put this one together. It asks for some different information. It's a lot more detailed. We'll just go through it too, and you can use whichever data sheet you'd like or feel more comfortable with. This one asks for the name of the irrigation system, asks you to check what type of irrigation system it is, whether it's center pivot, linear move. And I don't know how familiar you guys are with the sprinkler system, so I don't know if I'm going into too much detail or not enough, and so let me know. Linear move is basically like a center pivot, except it moves straight across the field instead of rotating around a circle. Solid set sprinklers, those are usually hand lines, or what you consider a hand move sprinkler, but you're not moving them. You have enough lines that you have one line for each set, and so you can just turn them on and off. Traveling guns, a big gun sprinkler that you can pull through the field, or sometimes they'll have a big roll where they can move themselves across the field. Hand move sprinklers are what we consider hand lines, side roll or wheel moves, or what we call wheel lines. Micro or drip irrigation, furrow irrigation is basically surface irrigation in furrows. Flood irrigation is another surface irrigation method. Energy source, whether or not it's electricity, diesel, gas, natural gas, propane, whatever the case may be. And then the cost of fuel. Type of drive unit, we talked about that yesterday a little bit. Direct drive, V-belt, whether or not it has a gearbox. We didn't really talk about belt drives yesterday. We looked more at close coupled and shaft drives, and some of those shaft drives would be your ones with the right angle gearbox. Direct drive would be close coupled, and V-belts, you'll notice, you'll see actual belts on the system, on the drive system, if that's what kind it is. Type of pump, centrifugal or turbine or submersible. We talked about all of those yesterday. They have some different categories of whether or not it's self-priming. We talked about flooded suction a little bit. Or if the lift is low, then the pump can prime itself. Or if it's non-self-priming and they have it broken out of whether the operating pressure is higher or lower than 40 psi. Pump information, similar to what we had on that other sheet. What's the pump flow rate? Here it asks where your pressure gauge is located. Is it at the center pivot? Is it somewhere out in the system? Is it right next to the well or the pump? And what is the pressure? Total lift, same as the other sheet. We talked about lift yesterday. And it tells you here distance from our surface during pumping to the wellhead or pump. And then it talks about elevation on the system. Generally on my sheet, I'll sketch out the system, and then I can look at Google Earth or something and get some general elevations later if I'm not measuring it. Here it's looking for estimated elevations from your pump out to your distribution point on your system, whether it's your pivot or your wheel lines or hand lines. Average annual total amount of water applied per year. That may be, I'm not sure that the farmer would, he may or may not know that off the top of his head. It's something that could be calculated based on the number of acres that are being irrigated and average flow rates. Average water application per irrigation event, you can probably get an idea of that. The center pivots, that's easier. They know how many inches they're putting down per evolution usually. and they may have an idea of how much water they're putting down with the set move or the systems as well. Application efficiencies, if known, probably won't be known, is what I'm guessing. Usually hand lines and wheel line systems have an application efficiency of 65%, where a center pivot would have an application efficiency of 85%. And they have a note here that it's the amount of water that you put on that's actually available for plant use or plant growth. And this data collection sheet is associated with an online savings calculator program, and their default to 85%, and that's obviously for center pivots. This asks for information about the pipe itself out to the system, what the pipe size is, whether the pipe material, A is aluminum, S is steel, P is plastic, and H is hose. And so you can mark what it is, how many feet. The fittings, you can drop those down here if you'd like. We talked about minor losses a little bit yesterday, just briefly. A lot of times that they are a minor part of the total dynamic head, and we can usually just use an average estimate of a few feet for those and be really close instead of calculating the minor loss through each valve, T, branch, meter, or whatever it may be, and we'll still be okay just because they are a minor portion of the total dynamic head. So this is where to go next. On the sheet, you'll have a copy of the full data collection sheet. If it's a center pivot or linear, it tells you to go to page 3. If it's solid set, hand move, or side roll, go to page 4. If it's a traveling gun, or furrow, or flood, or drip, go to page 4. So we'll go to page 3. And here it's just asking information about the system itself. What's the difference in elevation from the center of the pivot point to the outside edge, or from the end of the linear to the other end, or the highest point in the field? The pipe diameter is the actual pivot pipe. Is it aluminum, steel, or plastic? What's the span length on the pivot? How many spans are there? And what's the nozzle spacing in feet? That a lot of times actually varies along the pivot. For linear, it's more consistent. But you may or may not be able to get that. Tower drive motor horsepower. A lot of these pivots and linears will have electric motors out on each tower that drive the pivot, and you can mark how many horsepower those motors are here, and that gives you a good idea. If you look at historical usage, you can estimate how much power the pivot motor drives are using compared to what the actual pump is using if they're on the same utility meter. If an electric pump is not used, does the engine drive the generator as well as running a pump directly? What's the electrical cost per kilowatt hour? And we looked at that earlier. They just have it here again. Does the center pivot make a full circle, move 360 degrees around the field, or is the part circle pivot? You can drop that down here, and if it's a part circle, is it a half circle, is it a quarter circle, or three-quarter circle? You can put that all here. Pump efficiency, if known, chances are we're not going to know it. If we grab a pump curve for the pump, we know the approximate flow rate, we can get it from the pump curve. It's probably, if it's an old pump, it's probably less than what the pump curve would say. So that would generally be blank. Is there an end gun on the pivot or linear? Yes or no? If yes, how often is it on? If it has a booster pump, what size is the booster pump? And so a lot of end guns on center pivots will have booster pumps. And so the pivot can operate at a low pressure. But then you have this big gun, end gun on the end, and it needs a higher pressure to work, right? And so you'll typically put a booster pump on it to boost the pressure. This is page 4, where it said to skip to page 4. If you They're looking at a solid set hand move or side roll system, number of lateral branch lines. Pretty sure that just means the number of lines that you're operating at one time. Pipe diameter of the line itself. Generally, we are looking at either 4-inch or 3-inch on hand lines, 4-inch or 5-inch usually on wheel moves or side rolls. I haven't seen the other pipe sizes a lot on those. And the pipe material, generally it'll be aluminum. It can be something else, I guess. And how long are the laterals? How many sprinklers per lateral? Elevation difference along the lateral. Pump efficiency, again, if known. How many acres are irrigated? That's all fairly straightforward. And most farmers will know how long their laterals are, how many sprinklers there are. And we can always count those if we need to. Elevation difference, that might be harder to get, and the pump efficiency might be harder to get. And then the very last section, if it's a drip system, traveling big gun or surface, the only things we're looking at on those is pump efficiency and how many acres. All right, we got through the data collection sheets. Sorry if that was really boring.
Hey, Rick, let me ask you a question. Is there ever, do you always collect data just on a data, like a hard copy data sheet, or do you ever collect that via some type of data recorder or a computer or something like that?
We always use a hard copy paper sheet, and so we have laptops. I don't have any type of an iPad or a tablet type of system where it's just easy to hold in one hand, you know, and enter the information in. So I usually always get just a hard copy on paper.
Okay, great.
So, but you could do it either way.
And are you going to show us how you enter that information then into the computer? Is it just, do you have spreadsheets that kind of correspond to the questions you're asking there?
I do.
Okay.
And what I'll probably do, I don't have those in my presentation today. I was going to bring copies of my spreadsheets next week. And as we go through collecting the information and putting into the calculation spreadsheets, I was hoping to go through those then.
Oh, great.
So, yes, if that will work. And so, yeah, I will have copies of those, and we'll actually go through them next week.
Great.
Energy savings opportunities for pump systems. A lot of utilities will offer rebates, and they'll say if it saves energy and it costs money, well, there's a potential we could save or pay an incentive toward that project. There are certain energy-saving opportunities that usually are easier to identify than others. One of the major things that we can do is improve the pump efficiency. The pump may be old and it may be getting worn out, and it's just not operating very efficiently. We have tested some pumps, and they've actually had pieces of tarp or something caught in the pump impeller, and that's really cut down on the efficiency. So the pump itself wasn't necessarily worn, but it had some debris in the impeller, and so the efficiencies, our calculated efficiencies, were low. Another big opportunity for efficiency improvements is if the wrong pump is being used for the job it's doing. And I've seen this in several different ways. One system that we just looked at recently was a system where they had several deep well pumps, and at each wellhead they had a booster pump as well. And so the system was designed to operate with the well and booster, so the well would just lift the water to the surface, probably have 5 psi, and then the booster would boost it to 60 psi, the system operating pressure. What these guys did, they decided they wanted to save some energy, and so they just quit using their booster pumps, and they operated the system at lower flow rates. And so the system was working okay. All the pumps were running, and they were giving them the pressure they needed for the amount of the system that was operating, and that seemed to be okay. But we calculated pump efficiencies, and the efficiencies were really low. And we came back and got talked to these guys, showed them our low efficiencies that we calculated, and they were really surprised. They said, well, those well pumps, we just replaced the bows and worked on them, and they're only 2 years old. Why is the efficiency so low? And the reason is because they were designed to operate at a higher flow rate than they were operating at, and just lift that higher down the water to the surface with little pressure. But they were running clear to the left of their pump curve. We looked at pump curves yesterday. They were operating at lower flow rates, higher pressures, and the efficiencies were really bad. And so they're actually going to replace those pumps and put new pumps in that are designed to operate at the flows they're operating and pressures they're operating at the best efficiency point of the pump. And so the other thing you'll run into, a pump may have been designed to run hand lines and wheel lines, and they've replaced the hand lines and wheel lines with center pivots. And so the design, the operating conditions are a lot different than it was originally designed at, and so there may be energy savings opportunities there. It's just the wrong pump for the job. Another good opportunity to save energy is if the system's operating at higher pressures than it needs. Just mentioned replacing hand lines and wheel lines with center pivots. Typically, your operating pressures are a lot higher with hand line and wheel line systems. They need higher pressures to operate well than you need with center pivots. And so your flow rates may match up, but you're running at a lot higher pressure than you need, so there can be a good energy savings opportunities there. And you usually have a few different options. You may be able to trim your pump impellers. You may be able to remove stages if it's a vertical turbine pump and reduce your pressures that way but keep the same flow. You may be able to install a variable frequency drive, and then we'll talk about those a little bit today. If you're not familiar with the VFDs, they're called variable frequency drives. They're called variable speed drives. There are different styles. But basically, with a variable frequency drive, the main application that I see is you want your system to operate at a certain pressure all the time. Whether or not you're running at full flow, you'll be operating at full speed usually, your design operating pressure. But if you start reducing your flow rates, we looked at the pump curves yesterday, usually your pump pressure would increase. And you don't need those higher pressures at lower flow rates, and so a variable frequency drive will maintain a set pressure. That's the most common application. You program that drive to maintain a certain pressure at your pump all the time. It may be 50 psi, and no matter what's happening downstream, that VFD is going to try and control the speed of your pump motor to maintain that pressure. So, for example, if I have two center pivots operating on one system, and when they're both running, I have 50 psi, but if I turn one off, the pressure normally jumps to 80 psi. If I install a variable frequency drive on that system, if I turn one of those pivots off, the VFD will change the speed of the motor and slow it down so that I'm pumping that lower flow rate at exactly 50 psi. And I have some examples of VFD applications that we'll go through today, and we can take a look at that a little closer. Another energy saving opportunity with pumps, there may be potential to lower the pumping flow rate. Anytime that you are pumping at a higher flow rate than you need to be pumping at, you're using more energy than you need to be using. And so whether or not an easy fix is to replace worn equipment, fix leaks, and reduce our flow rate that way. We may look at the system flow against the required flow. Could we do the same job we're doing with the lower system flow rate and give the crop the water it needs? That may be the case in some instances. Pump tests. We do pump tests, and I don't expect that you will all be doing pump tests. We'll just be collecting what information we can out in the field. But a lot of times, my group will do pump tests. We'll go out there. We will measure the pumping flow rate. This this gives us the best information we can possibly get on a pump. We can calculate the actual real pump efficiency. And so just I thought it would be good to cover that today. So when we do a pump test, we'll measure flow rate. We have an ultrasonic flow meter that we can actually strap on the discharge pipe of the pump to measure flow rates. The system may have a permanently installed flow meter that we could use to get the flow rate, or we can estimate it based on the design flow rate of the pivots or how many nozzles are operating and at what pressure they're operating at. We'll measure the pressure at the pump. If there's a pressure gauge, we'll use it. We'll usually install our own pressure gauge just to make sure that it's accurate. Pumping lift, we've talked about that. We will use a well sounder. If it's a well, we can go down and measure the pumping lift. We can look, if we can't get into the well to get a measurement, we can look at the well log usually and see what our static water levels are and estimate a pumping lift based on that. Or if it's a surface water system, we can just use a tape measure and measure the distance from the water to the pump. Power use, as part of each pump test, we measure power use. Sometimes we can use a utility meter to make that measurement. On my sheet, I didn't really cover this. I'm going to go back really quick. I kind of skipped that part on my data collection sheet. Right here, we can measure the power use using the utility meter. There's a K sub H value, usually printed on the front of each meter. And then there's either, the old meters had a rotating dial. You may have seen that. And it would just rotate, and it had a painted strip on it, usually black or red, where you could count the number of rotations based on that strip. The new meters have a digital dial, and you just basically time. What we'll usually do is count how many revolutions, or we'll time 10 revolutions and see how much time it takes for that meter to make 10 revolutions. And then this meter multiplier, it's just a number printed on the meter, and this is basically the equation to calculate power use based on these inputs. And so we can use the utility meter to calculate power use while we're out there. The other thing that we can use is a portable power meter. I don't like to use those. If I can, use the utility meter just because it's a little more dangerous. You need to make sure you have the right safety equipment. That means you're getting actually into the pump panel. And you're measuring voltages and amperage, and so you need some training to be able to do that. But when we do a pump test, we will measure all of these things one way or the other. And then we can calculate the pump efficiency, and it's just basically how much work is the pump doing and how much power am I putting into it. And then the pump efficiency is calculated by dividing the pump output by the pump input. And just kind of along those lines, water horsepower, how much work is the pump actually completing, is flow in gallons per minute times total dynamic head in feet divided by 3,960. That gives me water horsepower. That tells me how much work that pump is actually doing. Then I can compare that to my input horsepower, and I can calculate the pump efficiency that way. Any questions about that at this point? I hope I'm not boring everyone. This is kind of exciting to a guy, an engineer that likes pumps and deals with pumps a lot, but I don't know how exciting it is to other people.
Rick, you're doing great. You're doing great. It's very interesting.
All right. I'd like to talk about VFDs for a minute. VFDs, at least in eastern Idaho, have been really popular lately. And they sure do make managing an irrigation system and operating it, they sure are nice for that. Like I said before, the most typical application is you set a pump pressure, and it just constantly maintains that pressure. Question here, are VFDs, are they the right choice? And it really depends on the system and the application. I have a couple of examples here. This is a system that has a 40 horsepower centrifugal pump. It's supplying water to one half-circle center pivot. The pivot's on sloping ground, And so the elevation change across the pivot at the high point is 130 feet higher than the low point. And it looks like the high point's probably in this area, and then the low point of the pivot's down here when it's down here. And so this is an actual project that was done. And what they decided to do, 130 feet of head, I'm just going to, is about 56 psi is the difference in pressure. And so this project, what they looked at is the flow is not going to change at all. It's not like the other scenarios we've discussed. The flow is going to stay constant. You're just pumping that one pivot all the time. When that pivot is facing uphill, you need a higher operating pressure to make it work than you do when it walks around and it's facing downhill. And so what was proposed for this system is that you put a pressure sensor on the end of the pivot, and that's what controls the speed of the pump. So when that pivot is uphill, your pump's going to ramp up and give you a higher pressure at the pump, give you the exact pressure you need at the end of the pivot. But when that pivot walks around and comes downhill, that pump speed is going to slow down, and it's going to give you just the pressure that you need. On a separate system I looked at similar to this, it was a gravity pressure pipeline with a booster pump that was supplying the pivot. When that pivot was downhill, the pump would just basically go into, so the VFD would put the pump in sleep mode, and the pump was basically turned off. They didn't need the pump at all. And then as that pivot would walk up the hill, it would start ramping up and give them the pressure that they needed. And so for this example, the pump is actually a centrifugal pump. But this example was put together to compare, okay, what if it was a turbine pump? What would be different? And this shows pump curves for two different pumps. You can see the vertical pump. These are blue lines. It's a little bit deceptive. Those are actually the horsepower lines. These off-colored lines are actually the pump curve lines itself. So you can see that this turbine pump has a steeper pump curve than this centrifugal that flattens out here on the lower end. And we talked about that yesterday as the difference. But anyway, in this example, we compare both pumps on this system. So just looking at the centrifugal pump at first, a pump test was completed on this pump. It was pumping 564 gallons per minute at 87 psi. That was the pressure it needed when it was uphill. And the pump efficiency was calculated and to be 76%. And so the pump's working good. The efficiency is a good, reasonable efficiency, so no worries there. But the proposal was to put a VFD on the pump and put the pressure transducer out at the end of the pivot. And so we always had the pressure we needed out there. The estimated energy savings for this project was 9,100 kilowatt hours per year. Cost savings of $241 per year. This is based on the utilities energy rates where we were operating. The cost of the VFD was $3,500. The incentive, the utility actually paid an incentive toward this project of $1,639, and then the payback after the incentive for this project would be 7.7 years. And this is on a really good VFD project. Just for a project, that's probably a typical payback. And so the same numbers were run. Okay, what if we use that turbine pump we just showed you? It's designed to operate under the same conditions. What would the payback be? And this, where it's a constant flow, the difference is just basically based on the pump curve. There shouldn't be a huge difference. Here the energy savings are slightly higher. The project cost is the same. The cost savings are slightly higher. Utility incentive was a little bit higher just because the energy savings were higher based on their incentive structure, and the payback was only 4.2 years in that situation. Now let's look at those same two pumps, the centrifugal pump and the turbine pump, but now instead of having a constant flow, we're going to go back to the example we previously talked about. Let's say we have maybe 4 wheel lines on this system or 2 pivots, and half of the season we only run half of the system. And so we're cutting our flow back instead of varying our pressures like we did on the other one that's constant flow. And so if we were to run that analysis for that centrifugal pump with the flat pump curve, and you were running it half flow, half the time, our energy savings would only be 1,400 kilowatt hours per year. Our cost savings would be $38 per year. There's no incentive just because it's not a good energy saving project, and this project would not pay for itself for 92 years. And so a VFD under that application on a centrifugal pump would not be a good idea. Let's look at that same situation with that turbine pump. Remember, the turbine pump has a steeper pump curve, so when you cut your flow in half, your pressures go a lot higher. The savings are a lot better in that situation. You end up with the payback basically of 7.8 years instead of 92 years. And so in this situation, a VFD would make sense. And that's the case a lot of times. If you're looking at reduction in flow to have a centrifugal pump, VFD doesn't usually make sense. With the turbine pump, it's more economically feasible. This is another completed project. And this is just a pump project. It's not a VFD project. This is actually a really good project, and I think it's probably a project that you might see in Montana in some of your areas. So this guy had a gravity pressure pipeline coming down from a reservoir or something. So he had some pressure, and then he had a centrifugal, 15 horsepower centrifugal booster pump that was connected to that line, boosting the pressure to a single center pivot. And I'm pretty sure he was just growing hay, and part of the time it was just an irrigated grass hay pasture. And what he was doing is, what we measured when we went out there was that he had 50 psi at his pump. His pivot was downhill from the pump. He had 76 psi at his pivot point. And so that's a lot more pressure than you typically need for a pivot. I'm pretty sure he needed only 45 psi at his pivot point to make it work right. We calculated the pump efficiency. It was 75%, which is really pretty good. And so we didn't have any efficiency recommendations necessarily, but we did identify that he'd be able to save energy by reducing his pump pressure. And so what we proposed is that he replace that 15 horsepower pump with a new 7.5 horsepower pump that would give him 25 psi at the pump and 50 psi down at the pivot. We estimated that the new pump's efficiency would be about 77%, so that's a little bit better than where he was at. He actually installed the new pump like we'd recommended. We went out after the fact and took more measurements. The new pump was operating at the design flow rate actually at 31 psi, a little higher than we'd estimated, but we found out, or the reason is because that the pressure in the gravity pipeline was actually higher that day than when we've been out there before. This just for this project compares what we had originally estimated in our initial report compared to the as-built conditions. The energy savings were slightly higher. His actual pump efficiency, if I flash back here, was 81% instead of the 77% that we'd estimated. And so his savings were a little bit higher. Cost savings were higher. We originally estimated this project costed around $4,900, as it came in at $3,200 or closer to $3,200. There was a utility incentive here. I wasn't supposed to show the utility name in my slides. I didn't take that out, I guess. But anyway, we'd estimated that the payback would be 3.4 years. Based on actual operating conditions, it was only 1.7 years. So this was a simple project. He's just pumping at more pressure than he needed. Replace it with a smaller pump up at the pressure you need, and it paid for itself in under 2 years. And so that's a pretty good return on investment. After 2 years, he's just saving $565 per year. There's a picture of the project. That's the new pump. He just basically bolted it in place of the old pump. The new pump's bolted in place here. The old pump's sitting there in the off to the side. This is another completed project. This was a 300 horsepower vertical turbine pump pumping out of a river. Pump test was completed. It was pumping about 2,900 gallons per minute at 113 psi. So they're pumping out of the river up to the farm. That's why the pressures are pretty high here. Measured the power use and calculated the pump efficiency to be 68%. So that's pretty low. So the recommendation here was that you replace the existing pump with a new pump. The new pump was installed, the same horsepower, but now we're pumping a higher flow rate, 3,470 gallons per minute, at a little bit higher pressure, using just a little bit less power. And so, but the new pump efficiency is 85%. And so really the energy savings here, you can run with the higher flow rate, same pressure pretty much. You can run more of the system at one time at the same demand in kilowatts, but you don't have to run as many hours now because you can run more lines at one time and get over the system quicker. There's a picture of the project. The pump in the middle is the new pump. And this is evaluation. Originally it estimated, what was originally estimated is that the flow would be about the same instead of higher. And anyway, the energy savings ended up being quite a bit higher than originally estimated for this project. And the payback ended up being a lot lower. So 2.3 years compared to 5.8 years like it was originally estimated. And so that's another good project. Third example, this is a 30 horsepower short coupled vertical turbine pump. Flow rate and pressure were measured. The efficiency was calculated, and it was 53%. That's really not very good. And so recommended that they replace the pump, but this pump was actually running 2 wheel lines on 80 acres. In order to cover that ground, they really needed 2 more lines in order to get over it and adequately irrigate that ground. So the recommendation was that they install 2 new wheel lines and install a new pump. What they ended up doing is deciding to install a new center pivot, half-circle center pivot, get rid of the wheel lines, and then they didn't actually replace the pump on this system. They worked on the pump. They did some work on rebuilt the bowls and did some new bearings and that stuff. So they didn't get their efficiency up as high as they probably could have with the new pump, but they improved it to 65% instead of 53%, which is still a really good improvement. These are just pictures that doesn't show too much. This is the pump before. It was irrigated by wheel lines. That's a new center pivot. And this is the project energy savings, 17,000 kilowatt hours per year, $446 per year. One thing that was interesting feedback, I wasn't told this directly, but there was some feedback from the customer to a conservation district person, and they had doubled their yield on that farm by completing this project. They're really skeptical because the pivot cost so much money, and so they were really a little bit nervous about installing the project. And so energy savings was just one portion of the benefits of the project. The other portion was that they increased their yield. Now they could put enough water on to get a good crop, and they actually doubled their yield, so that was good. I have one more example. And if my clocks, we're almost out of time. We've got about 5 minutes, but I think we have time to run through this one. This is a VFD example. This system, they had 2 center pivots running off of 1 well, and then they had some hand lines on some grass pasture. The system, the pump was designed to run both pivots, but there was a significant part of the season that they were only running 1 pivot. They estimated about 66% of the time. So they would usually plant 1 pivot in potatoes and 1 in grain. So when the grain was done being irrigated, they'd just be irrigating potatoes for the rest of the season. Our recommendation was to install a VFD on the pump to control pressures or reduce flow rate. What they had done previously is they just had a valve at the pump, and they would throttle that valve so that the pump's still operating at a high pressure, but they're burning the pressure through the valve, and the system was seeing a lower pressure, so they wouldn't damage their main lines and their pivots. With the installation of the pivots, we took measurements with the VFD running and without, and the total calculated energy savings for that project was 84,300 kilowatt hours per year, or their current rate at the time, cost of electricity, they'd save about $3,414 per year. I think I showed it was a 250 horsepower pump. I didn't really mention that. So it's going well pump. And then this is just a project cost analysis. That project cost $37,000. Big VFDs are expensive. And that's why on some projects it's hard to get a good payback. But we're saving $3,414 per year. Without the utility incentives, the payback was 11 years. With the incentive, it's 8 years. There are additional benefits of a VFD besides energy cost savings. It makes it easier to manage the system. You avoid overpressuring your system, and there are some additional benefits that we don't really factor into the total cost savings. VFD energy savings depends on a number of factors. What percent of the time does the system operate at a reduced flow rate? Oh, sorry about that. If it's a significant percentage of the time, the VFD may make sense. If the system runs at full flow most of the time, you will use more energy with the VFD than you would without. VFDs are not 100% efficient, and so you have some efficiency losses there. And so if you're running at full flow the majority of the season, that's probably not a good option. It depends on how much the flow and pressure varies across the system. It depends on the pump curve. We could see that with the example of the centrifugal pump versus the turbine pump when we started cutting back on flow rates. The other thing it depends on is what your energy prices are and the pressure reducing potential. If the system would operate at 130 psi without a VFD, or your pump would, as opposed to a pump that would only operate maybe at 65 psi at reduced flow, you'll see higher energy savings the farther you can reduce that pressure. And so that is basically what I have for today. And Mila and Sarah, I sent an email just letting you know that I pretty much have covered most of the information that we wanted to cover in these 3 presentations in 2 presentations. So I would maybe recommend if there's anything else you would like me to cover, we could do that tomorrow, or we could just cover it when we meet next week, whatever you think would be best.
Well, Rick, first of all, thank you for those for your presentation today. Those examples were excellent, and it seems to me that we would be able to, you know, carve out a little bit of time or add on a little bit of time at our in-person training next week if we had some follow-up questions or if there was other things we needed to go through that come up during the regular training. What do you think, Sarah?
I would agree with that, but I also would like to open it up to everybody else. If there's specific issues that you're worried about or that you think you need more in-depth information on, either throw us a chat or send us an email and we can make sure we get those issues addressed.
Are there any other questions about the information we just covered or the projects that we talked about?
It's a quiet group today, but I'm sure there'll be plenty of questions when we're all sitting down together.
Yeah, like I say, this is, yeah, when we're sitting face-to-face, it'll be easier to answer and ask questions too.
Yeah, there is definitely a level of awkwardness with the webinar format.
Yeah.
The other option that we might have is after we've done our in-person training, if we want to hold off and not do a webinar tomorrow, we could see if after we go through an actual scenario where we're trying to fill in the data sheet and are in the field, you know, if we find something we need to cover in greater depth, maybe we add a webinar on later.
That's a good idea. Yeah.
Yeah, good idea. Okay, well then,
otherwise,
yeah, go ahead.
Oh, I was just going to say, otherwise we'll put the recorded sessions for yesterday and today on that website that I sent out to you in email. You'll find other training materials there that we'll be going over in class, but you can look for the recorded versions there as soon as we have them available.
Great, and I will email you a copy of this presentation I went over today just right after we get off the phone.
Okay, thanks, Rick.
All right. Well, it sounds like with that, we'll see everybody next week in Phillipsburg.
Sounds great. I look forward to it. Thanks.
All right. Thanks a lot, Rick.
Right.
It was a great webinar.
Well, thank you.
Safe travels, everybody, out to Phillipsburg.